As of July 2025, Western defense analysts and aerospace experts continue to view the Su-57 as a platform that incorporates partial stealth features but does not meet the standard definition of a full-spectrum low-observable fifth-generation fighter. The Su-57 has now entered limited production and early service within the Russian military, with an estimated fleet of around 20 to 24 aircraft. Despite ongoing upgrades and continued public claims by its manufacturer regarding stealth and avionics advancements, credible Western sources maintain that the aircraft falls significantly short of the stealth capabilities demonstrated by other aircraft designed under a true low-observable doctrine. The Su-57 uses design elements intended to reduce radar cross-section, including internal weapon bays to limit external reflections, moderate edge alignment on the wings and fuselage, and radar-absorbent materials across key surfaces. Its cockpit canopy is coated to reduce radar bounce back, and there are additional composite structures intended to mask radar return from certain angles. These design choices show an effort to reduce the aircraft's signature from the frontal arc, which is a critical element in survivability during beyond visual range (BVR) engagements. However, Western experts highlight that these measures are relatively limited when compared to what is seen on other operational stealth aircraft. One of the most criticized aspects is the Su-57's rear fuselage and engine layout. The aircraft retains exposed, circular engine nozzles, which present a large radar and infrared signature, particularly from the rear and bottom angles. In contrast, true low-observable aircraft typically use flat or semi-shielded exhausts and incorporate advanced nozzle shaping to reduce the radar return and heat emissions that can be tracked by both radar and infrared sensors. As of mid-2025, publicly available radar cross-section (RCS) estimates continue to put the Su-57's average signature between 0.1 and 0.5 square meters. This is significantly higher than the radar signatures of more advanced stealth platforms, which operate with frontal RCS values in the 0.0001 to 0.005 square meter range. These estimations are derived from digital modeling, computer simulations, and visual inspections of the Su-57's physical design as it appears in open-source imagery. Multiple sources, including the War Zone, Aviation Week, CEPA, Center for European Policy Analysis, and RAND Corporation, have analyzed the Su-57's layout and conclude that while it may achieve some radar reduction from head-on, it is not sufficient to evade modern multi-band radar systems. Another issue concerns the Su-57's integration of external sensors and antennas. These components are critical for advanced situational awareness, but unless fully embedded or carefully shielded, they increase radar signature. In several flight tests and air parade appearances, the Su-57 has been observed carrying external pods or with visible sensor bulges, suggesting compromises in the design that reduce its stealth profile in operational conditions. While newer builds may include updated features, there is no confirmation from credible sources that these changes have dramatically altered its radar or heat signature. In addition to the physical design limitations, the aircraft's real-world operational deployment patterns further reflect concerns about its stealth performance. Throughout multiple conflict zones and exercises since 2022, including those occurring during the Ukrainian conflict, Su-57s have been deployed in very limited numbers. When they are used, they operate at extended ranges, often launching standoff munitions well outside contested airspace. There are no credible reports confirming their penetration into highly defended zones. In some cases, the aircraft has flown with radar reflectors installed, a practice that further undermines stealth but is often used for safety and training purposes. This suggests that the Su-57 is not being risked in environments where its survivability would depend on being truly undetectable. Another key point highlighted by Western technical journals is that the Su-57 was designed with a different emphasis than low-observable first fighters. While it does include elements to reduce radar signature, it also places strong emphasis on supermaneuverability, high-speed performance, and multi-sensor tracking, including long-range radar detection via L-band side arrays. These features suggest the design philosophy prioritizes detection and engagement of stealth aircraft from distance rather than evading radar itself. However, the use of L-band radars, which are broader in wavelength and less precise, does not compensate for the aircraft's inability to avoid detection by high-frequency fire control radars. On the propulsion side, the Su-57 still relies on engines developed from the older AL-41F1 series. A second-generation engine known as ISDELIA-30 has been under development for years and is intended to deliver both higher thrust and reduced infrared and radar signature. Yet, as of July 2025, there are no confirmed operational aircraft flying with the full capabilities of this engine. Prototypes have been seen with test variants, but production aircraft in service do not appear to benefit from these supposed improvements, and no dramatic reduction in thermal or radar profile has been observed through either satellite imagery or close-up inspection during public events. The current state of the Su-57's production also limits any major stealth gains. Russia's defense manufacturing sector continues to face severe constraints in producing high-quality RAM coatings, composite materials, and tight-tolerance assemblies that are critical for effective stealth. These industrial challenges mean that the consistency of stealth performance between aircraft is questionable, and each production batch may vary in quality. Regarding export status, a few units are scheduled for delivery to a confirmed international buyer in 2025. This export version reportedly retains the same airframe structure and stealth design as the domestic model. There is no indication that any major redesign has been implemented to enhance the aircraft's radar signature performance for foreign customers. Western observers note that this further indicates the limitations of the current design, as typically export models are downgraded rather than upgraded. Western military institutions and technical research outlets maintain that stealth is not simply about shaping and materials but a complete system architecture involving passive sensor usage, emissions control, heat masking, precision manufacturing, and all-angle signature management. From that systemic perspective, the Su-57 is not considered to meet fifth-generation stealth standards. Rather, it is more accurately described as a fourth-generation plus aircraft with some stealth features or a hybrid design intended to bridge technological gaps. Finally, the aircraft's long-term survivability against evolving radar and sensor networks is uncertain. Western and allied countries continue to invest heavily in stealth-defeating technologies, and without a significant leap in Su-57 design or production quality, it is unlikely that it will remain competitive in environments with advanced airborne warning, long-range radar tracking, or integrated ground-based air defenses. All up-to-date and credible Western technical assessments agree that while the Su-57 represents an evolution in aircraft design and includes some stealth-enhancing features, it does not possess the full low observability characteristics required for operations in high-threat airspace. Its vulnerabilities in rear and side aspects, reliance on older engines, inconsistent production quality, and cautious deployment patterns point to a platform that, while modernized, cannot yet be classified as a true stealth fighter by current Western standards.